Hello all, this is Mohammad Hanif. Once again, welcomes you to this lab session on digital signal processing. So today, we'll be designing low-pass FIR filter in Matlab. So let's start. CLC, clear all, and then close all. So here the basic idea is to first we'll be designing one impulse response for low-pass filter, and then we'll design or we'll generate two different signals, namely x1 and x2, and then either we'll try to add those two signals, and we'll see that x1 and x2 having two different frequency bands, and then after doing filter on these two signals, we'll try to get the signal which is having a low frequency, and or we can say that which is under cutoff frequency, that frequency will be uh, available in the output of the filter. So starting with designing with uh, cutoff starting with sampling frequency. So input, enter the sampling frequency, and then taking TS as 1 upon Fs, and now we are taking cutoff frequency. So input, enter the cutoff frequency, and this cutoff frequency, it will be in analog format. So here we can write that analog frequency. To convert it in digital frequency, we will define as omega c. So omega c, it will be 2 into pi into fc by fs. So this will gives you equivalent digital cutoff frequency. Okay, and so starting first we have to design one impulse response. So as we are trying to design with a FIR filter, we'll be having a little selected span of the frequency. So first we're defining that as L, input, enter the length, and this length must be in odd number as we are writing program in Matlab, and here the index 0 will not be included, and negative part of the signal also will not be defined here. So we'll try to define one odd number, and that where we can try to frame this filter coefficients from negative to positive side. So here we basically we do need of odd number, enter the length of, we say that FIR filter. So is actually we can say as a window size, right? And then defining h of n. So h of n, it will be having the zeros, the length of L. So 1 comma L. And then, so as I said that we do we are why we are taking this odd number means to try to we are trying to frame it filter coefficients in one window. So where as index starts if you consider the original one, which will be having the negative side as well as positive side, including the zero, that zeroth part, it will be the center in this odd number. So we'll define that here, C as a center, and how we can get the center value for this L, so L plus 1, and then divide it with 2. Now defining Hn, starting with for loop, and defining n is equals to, starting from 1 to C minus 1. So first we try to define the negative side of filter. So negative side means the h of n is equals to, so here filter response for low pass filter, FIR filter, is sine omega c into n by pi n. So we have to define that here. So this is basically a sync pulse. So here we'll write sine omega c into n minus c, and this value will be divided with pi into n. So n means n minus c, and end. And this will be the negative side, and at 0, 0 will be at exactly at center. So that center value will be h of c is equals to, we'll define it with omega c by pi, or else it will take as a 0 here. So that's why. And next, for the positive side, again we need one for loop, and we start with k is equals to 1, and the length of it will goes up to the same c minus 1. And here, as already we have negative side, and the same negative side will be equal with this positive side. So as depends on the symmetry property, here we can write h of c plus k will be equal with h of c minus k. So n. Now we can define, or we can design a plot to plot this one. So for plotting, we do need one length. So we'll take as n, starting from 0 to L minus 1. So here we are trying to index start with 0, as in just plot, it will just display with 0. Okay, so that's why we are writing L minus 1, or else we would have written 1 to L. Okay, so writing the first figure, figure 1, the stem n comma h, with respect to n will be plotting h values. Okay, so we'll be having labels called x label. X label will be n values, and y label will have h of n values, and the title for this will be causal impulse response of FIR LPF, right? So we'll try to run it up to here, and let's see how we get the impulse response. So entering the sampling frequency, taking here 8000, and enter the cutoff frequency, let's say 2000, and enter the length. So let I'm giving 51. So this is impulse response, right? So this is, see here, you can see that index is displaying 0, and it goes up to 50. And if you include that this 25th part, so totally if you start with 0, so totally the length will be 51. Okay, now continuing the program, will, if the this size is So as we are taking the 51 only, so after doing a low pass filter, the signal accuracy will not be great. So if you want, you can take the 256 samples. So here we can write that also. So n uh, log base of 2 with capital L, and then so log of L means whatever the value you gives here, it will comes in fractions. So we'll try to make it round off with this keyword seal. Seal means sealing it to a round off value. So here seal of n, and then taking capital N, say max. Max means it will take the maximum number from the defined two values or some values. Okay. So here said 256 comma 2 power n. So in this, whichever is maximum, it will take that. And now we'll calculate FFT for the small h. So FFT of small h with respect to n, and then k is equals to 0 colon n minus 1. So once again, we'll try to plot another figure, okay, for filter. Okay, so that's why we are taking here k starting from 0 and going up to capital N minus 1. So figure 2, and here let's plot it with 3 comma 1 comma 1. So we'll have uh, three plots. The first plot for stem k value with respect to k, we'll draw absolute value of capital H. And then labeling for this X label will be capital K, Y label it will be absolute values of H. Okay, right. And this title for this one will be, it will be the magnitude response, response. How we got this? By doing FFT. So we got with DFT of FIR LPF. And next we shall have a digital frequency also. So that's why we'll write omega is equals to start from 0, then with the with the steps of 2 pi by n, it goes up to 2 of 2 pi by n. We'll put this in bracket. Okay. So normally digital frequency will be framed from 0 to 2 pi. So that's why we are writing here 0 to 2 pi. Okay. And taking omega is equals to omega by pi, and now subplot. So this is will be 3 comma 1 comma 2. Okay, this is the second one. And here we'll try to plot it with W and absolute value of H. Okay, and x label for this one will be omega by pi. Yes, and then y label for this one, so y label will be the magnitude. So how we got this magnitude? From the uh, absolute value of h e power j omega over j omega, isn't it? So this will be magnitude, and then title for this is magnitude response with DTFT of FIR LPF. Okay, and we'll be having a third plot for equivalent analog frequency. So for that one, we'll take small f, and it will start at 0 fs by n and goes up to fs minus fs by n, right? Defining the subplot. So here 3 comma 1 comma, and it would be 3. Yes. So here we'll try to plot f comma absolute value of h, and then x label will be frequency in hertz, because this is in analog, and y label will be just h of j omega, right? And this will be magnitude response. What is this? This is equivalent analog LPF, magnitude response of equivalent analog LPF. So we'll try to run up to here. So save it and then run it. So once again, starting with 8000 sampling frequency, and cutoff frequency as earlier 2000, and then 51. We got error at 38. So this is the first one. I will say 38. So omega W is having 0.6. Okay. 38. So here in here we made a mistake. So 2, it will be 2 in up to 2 pi, and then we have to minus it with 2 pi by n. This is correct. Now if we run once again, so 8000, and then cutoff frequency will be 2000, and then size is 51. So here the second figure you can see here. So this is the impulse response, and then the magnitude response of this one is given here. So here you can see that we wrote here 256 So in this, as we have given 51, the maximum value will be the 256. So that's why the plotting is done up to 256 here. It comes up to 256, and the middle value it will be omega by pi. And here you can see that this is the uh, analog cutoff, analog low pass filter plotting. So here you can see that this is the cutoff frequency we are displaying here, 2000. Okay, now so designing the impulse response is over, and now we have to design two signals, namely x1 and x2. So starting with NTS. So NTS will be required for generating two signals. So starting with 0 to t, and the value will be in with the intervals of TS and 1 minus up to TS. Okay, and then so first F1 taking the first frequency. So say input, enter the frequency for the frequency of first signal x1. Okay, and next F2. So same, but this one will be x2 and this one will be second signal. Okay, so defining x1 as cos of 2 into pi into f1 into nts. Copying this, and next making as f2, and this will be x2. Okay, and then calculating x. So here I'm adding two signals x1 and x2. We can do any mathematical operation here. We can do multiplication or division. So depends on that we are going to get a second signal. If we do multiplication here, it will be DSBSE of those two signals, and then later we can do filter to recover either x1 or x2. So in this x1 and x2, whichever there is lower frequency and which is under the cutoff frequency, that will be available at the output of after low pass filter. So here we'll try to give two different frequencies f1 and f2, where we try to give f1 as less than cutoff frequency and f2 as more than cutoff frequency. Okay, now defining y1. So y1 here we try to accommodate it with the uh, convolution of uh, our impulse response with x1. Similarly, we will be having y2, where we try to do the convolution in with respect to h with h2 x2. Similarly, we will be having y, that is also a convolution of h and x. Okay, so here first y1. So for that one we need zeros 1 comma ns. So 1 comma, it will be this maximum value, that will be n. So here 1 n. So we'll copy this and we'll change this as a y2 and this as a just y. Now we need to do filtering, right? filtering operation on using convolution, right? So here we will be writing that program. So for n is equals to, so normally we start with index 1, but here we'll try to take the index start from the size of L. So we'll go with this size, okay? So starting from L and then goes up to capital N, okay? So this capital N is our, so it is the maximum value between the, so here, okay? So either it will take 256 or more than 256. If the length is more than 256, then the n value will be 2 power of small n, okay? So and next taking another for loop. So here k is equals to start with 1 and it goes up to length of L. So already we have seen in the previous video how we can write the convolution program. That is, first we'll try to write with y1 of n is equals to y1 of n plus, and here comes the uh, convolution program, h of n into x of, so x1 of n minus k plus 1, okay? So we'll copy the same thing and paste it here. So this will be y2, this will be y2, and this will be x2, and this will be just x, this will be just y, and this will be just y. So here this is for convolution of our x1 signal, and this is a convolution with respect to x2 signal, and this is the convolution with respect to third signal, that is x1 plus x2, okay? And we'll end it here and end, okay? So filtering is over here. Now just we have to plot and see how many plots we can make here. So for every signal we'll draw x1 and then y1, x2 and then y2. So we do need 6 plots. So starting with say figure 3 here, and then subplotting it with 3 uh, 3 rows and then say 2 columns, and then starting with 1. As I said that we need 6 subplots, and then first we'll try to plot with x1, and x1 is starting at L, okay, with some L plus some values. So we can either you can go with 256 or any other value. So I'm just taking 250 here, some random number. You can take any other value also, okay? And then x label. So in x label we'll be having just small n values, okay? So n. Then y label. So y label will be input signal, and input signal x1 of n, right? And then title, no, title, so title will be input, so this one will be just x1 and 1, and here we can say input signal x1 of n. Okay, so first plot is over. Now we'll copy from here and then paste it here, and then first change this to second plot, and here second plot will be y1 of n, right? So here it will be having same n values, and x label will be uh, y1 of n, and this will be this is the LPF for LPF of input signal x1 of, right? So because y1 is consisting of convolution of x1 and h of n, so that's why it will be the low pass filter, right? And next pasting it once again. So this time this will be the third, and instead of x1 we'll go with x2 here, and this will be x2, and this will be x2. Similarly, pasting one more time, and this time this will be fourth plot, and this one will be y of 2, right? I will change that y of 1. Okay, y of 1 x2, and y2, and this is n, and this is y2, and this will be LPF of input signal x2 of n. All right, and pasting one more time, and say this is fifth one, and here instead of x we'll try to x, and this is not input signal, this is the addition of two signals, right? This is a combination of input signals x1 of plus x2 of n, right? And then pasting it for the final time, this will be the 6, and it will be the x, or this will be y, and y, and this is LPF of input signal x. Okay, right? Now this is it, the done, the program is over here. Now we'll run and we'll check what will be the response. Now once again running it, so entering the sampling frequency 8000, and cutoff frequency here let's go with once again 2000 and 51. Okay, so here till now we have seen, so this is impulse response, the first figure, and then second figure this one, and next here we have to, it is asking the enter the frequency of, so as we have given the cutoff frequency as 2000, so cutoff frequency we have the given 2000, so we have to remind this, and so x1 I am giving 500, x2 let's go with more than 2000, so here we'll give 3000. Not error at 74. Okay, so the error, so here we have to define n ns as the length of nts. Okay, and instead of n here we'll write ns. Okay, So this will be ns. Okay, now once again we'll run the program. So here sampling frequency 8000, and then cutoff frequency is say 2000, size is 51. So here up to here is, so we have seen already, right? Now giving the first frequency as 500, and then next is 3000 more than 2000. So here I'm going with 3000. So here you can see 500 and then 3500. So here these are the outputs. So here you can see that this is the first signal of frequency of 500, okay, and this is the LPF output. So when here the signal is 1, here you can see that because this 500 is under the cutoff frequency 200, so we can see the gain is almost equal with the same as input. And next, here we are giving designing X2 signal, and here the input is 1, and here you can see that the gain of this one is 0.01. That means the frequency is above the 3000, above 2000 cutoff frequency, and this is x1 plus x2. So some random signal is generated here, and from this you can see that x1, the which frequency is having less than cutoff frequency is available here. Okay, so I hope you understand this. So this is the first impulse response of the signal, and then this is the according to filter coefficients we have drawn this, and then this is the we have taken two signals x1 and x2, and then we have run filtering on these two signals. Okay, thank you.